Friends, I welcome you in the lecture on functional analysis course. Today we will define the quotient space n by m, and we will see that n by m is also a complete non-linear space. That is, n by m is also Banach space. Here n is non-linear space and m is closed linear subspace of m. Closed linear subspace of m. N by m consists of all cosets of the form x plus m, where x belongs to n. X is vector in n and x plus m is equal to the set of all vectors of the form x plus m small m, where m belongs to m. Recall that x is a vector in n and small m is vector in m. So n by m consists of all these cosets. N is non-linear space, m is closed linear subspace of n. Sorry, here I should have written m is closed linear subspace of n. Now we want to prove that n by m is Banach space. So in order to prove that n by m is Banach space, we must prove that it is closed norm-linear space, and we will define norm on n by m as norm of x plus m, where x plus m is member of n by m, as infimum of norm of x plus m, where m belongs to m. So it is infimum of all such a norms. Such a norms means norms of these types of vectors x plus m. So norm of x plus m is defined as like this. We want to prove that n by m is Banach space. For clarity, let me take this, repeat these things and take this as a theorem. I'll repeat the things and take this as a theorem. So our theorem: let n be a norm-linear space. Let n be a normed, you can use standard abbreviation NLS. Let n be a norm-linear space and m be a closed linear subspace. M be a closed linear subspace of m, of n. What do you mean by closed linear subspace? N is non-linear space, hence it is metric space, and M is closed linear subspace, means it two things: it is linear subspace of non-linear space n, and secondly it is closed subset of metric space n. Remember that as every normed linear space is metric space. So by closed we mean it is a closed linear subspace of N. The set N by M is defined as N by M is equal to set of all quotients x plus m where x belongs to n. It is a normed linear space. The norm on N by M is defined as norm of x plus m is equal to infimum of norm of x plus m. I should write small m to denote the fact that m is vector in M. Norm of x plus m where m belongs to M. Then N by M is complete normed linear space. N by M is complete normed linear space. So in order to prove that N by M is complete normed linear space, we will use the standard outline which I told you in second lecture. Let x plus m and y plus m belongs to N by M. Here x and y are vectors in N, and we are considering the cosets x plus y and y plus m in quotient space N by M, and alpha be a scalar. Alpha be a scalar. First, we will verify 4 properties of norm, and then we will prove that N by M is complete metric space or complete normed linear space. So first property of norm of any vector, in this case we take a vector norm x plus m in the quotient space N by M, is non-zero. So norm of x plus m is infimum of norm of x plus m where m belongs to M. It is infimum of this set. As norm of this vector is non-negative, so every member in this set is non-negative. Hence, the lower bound or greatest lower bound of this set will also be non-negative, which implies the fact that it is greater or equal to 0. So this is obvious, because if every member of the set is non-negative, then the infimum of that set will also be non-negative. So we are done with first property, that norm of any vector is non-zero. Second property which we will prove is triangle inequality. Norm of x plus m plus y plus m. By definition, this is equal to, by definition of addition of cosets, this is equal to norm of x plus y plus m. Now by definition of norm, this is equal to infimum of the set norm x plus y plus m. It is equal to infimum of norm of x plus y plus m, where m is vector in M. This is less equal to let me rewrite this as this is equal to infimum of norm of x plus m dash plus y plus m double dash, where m dash and m double dash belongs to M. Make sure that you understand this step. It follows from the simple fact that any vector we can write it in the form m dash plus m double dash. The choice of m dash and m double dash may not be unique, where all these three vectors m, m dash and m double dash are in the set M. This choice is not unique, but we can write any vector m in this form. This is equal to infimum of, I'll use triangle inequality and write this as infimum of norm of x plus m dash belongs to M plus infimum of norm of y plus m double dash, where m double dash belongs to M. Which property we have used? Triangle inequality. Since norm of x plus m dash plus y plus m double dash is less equal to what? Norm of x plus m dash plus norm of y plus m double dash. This is equal to norm of x plus m and norm of y plus m. Third property which we will prove is norm of x plus m is equal to 0. What is 0 element of n by m? It is 0 plus m, which is equal to m itself. So 0 element of the quotient space n by m is 0 plus m, which equals to m. So we want to prove that norm of x plus m is equal to 0 if and only if x plus m is equal to m, that is 0 plus m. So norm of x plus m is equal to 0. This implies that infimum of the set norm x plus m is equal to, where m belongs to M, is equal to 0. So by definition of the infimum, from real analysis, you must be knowing the definition of infimum. What is definition of infimum? Let me recall this definition as we need it here. If we have a lower bounded subset, a non-empty and lower bounded subset non-empty and lower bounded subset of set of real numbers non-empty and lower bounded subset of real numbers, then the number g is called infimum or greatest lower bound of S if it satisfies two properties. So first property is that it should be lower bound at first place. So g must be less equal to x for all x belongs to S, and secondly, no number greater than g can be a lower bound of S. Mathematically, we express this as for every epsilon greater than 0, there exists y belongs to S such that y is less than g plus epsilon. So g plus epsilon is number greater than g and it cannot be lower bound of S. I'll write it in words as well, that is no number greater than g, no number greater than g can be a lower bound, of S. So here we see that greatest lower bound is 0. So g will be 0 plus epsilon. Epsilon we can replace by any positive real number. In this case, we will take epsilon to be 1 by k, or let us take okay, let me simplify the things. Why I'll take mk, and it is say less than, I'll take it to be 1 by k itself. This choice is not unique of epsilon. I may take 1 by 2 raised to k as well. Any choice will work. So this implies this holds for every positive integer k. This holds for every positive integer k. Okay. So thus there will be a sequence, say mk, such that mk plus x or x plus mk will be less than 1 by k, and note that 1 by k tends to 0 as k tends to infinity. So by using this observation, we will say that mk converges to x, and then we will use the closedness of n. Okay. So this implies there is a sequence mk such that is a sequence mk such that norm of x plus mk tends to 0 as k tends to infinity. I have justified this step, explained it in detail. You take k or 1 by k or 1 by 2 raised to k, and we can observe that there exists some sequence mk by using definition of infimum. So remember that in this step we are using definition of infimum. This implies I could write this step as there is a sequence mk in M, I should say, because mk exists in M. It is of course in M. So this implies that I could write this as mk minus x tends to 0 as k tends to infinity. By definition of limit point, mk is a sequence in M. M is subspace of metric space N, and it converges to some point x in N. So by definition of limit point, it converges to minus x. So by definition of limit point, by definition of limit point, minus x is limit point of M. So this implies minus x is limit point of M. This implies minus x belongs to k. Why is it? Since M is closed and a subset of metric space is closed if and only if it contains all its limit points. Also, X is linear space, so X belongs to M as well, since M is linear space. So one way implication we are done. To complete this, let me finally write x plus m equals to m. You know from linear algebra, x belongs to m if and only if x plus m equals to m, and this is nothing but 0 element of n by m. To be precise, I can say 0 plus m, which is 0 vector of n by m. So thus we proved that if norm of x plus m is equal to 0, then x plus m is 0 element of n by m. It is 0 vector. If you carefully observe this argument, you can see that all steps can be reversed back. So we have if and only if norm of x plus m is equal to 0 if and only if norm of x plus m is 0. I repeat, norm of x plus m is 0 if and only if x plus m is 0 vector in M. Okay. Now fourth property which we will prove is this. About scalar multiplication, norm of alpha x plus m. This is the fourth property which we will prove. Be slightly careful while reversing back the steps. You may need to mention that there exists sequence mk with some little change of mentioning the facts. The reverse wave proof also will work. Okay. Fourth step, alpha is scalar. Recall that we have specified alpha to be scalar, and it is fairly easy to observe this. last property, norm of alpha x plus m. By definition of scalar multiplication, this is equal to norm of alpha x plus m. This is equal to infimum of norm of alpha x plus m, I should say small m, where m belongs to m. This is equal to, I could replace m by alpha m as well. This is due to the fact that M is linear subspace, and since alpha m belongs to M, provided alpha is non-zero, alpha m belongs to M if and only if M belongs to M, as M is linear space, assuming that alpha is non-zero. So this I could write it as infimum of norm of, say, mod alpha, I will take outside, norm of x plus m, m belongs to m. Why this is so? Because m is linear space. As mod alpha is non-negative, I could take it outside this infimum of whole set. So note that this is not always true. We cannot take constant outside, but as it is non-negative mod of alpha, I could take it outside and write this as norm of x plus m, m belongs to m. So this is equal to mod alpha norm of x plus m. This proves the scalar multiplication property of norm. Norm of alpha x plus m equals to mod alpha norm x plus m. So we are done with the four properties of norm, and thus we can say that n by m is norm linear space. N by m is norm linear space. Now we want to prove that n by m is complete norm linear space. That is, next we want to prove that n by m is complete metric space. So one of the definition of complete metric space is, a metric space is complete if every Cauchy sequence has convergent subsequence. N by m is complete metric space if every Cauchy sequence has convergent sequence. So let us take some Cauchy sequence in n by m. We begin by taking a Cauchy sequence. Take a Cauchy sequence in n by m. Take a Cauchy sequence in n by m. It is easy to observe that this Cauchy sequence in n by m will have a subsequence of the form xn plus m such that norm of xn plus m minus xn plus 1 m is less than 1 by 2 raised to n. Let me write it clearly. This Cauchy sequence in n by m, this Cauchy sequence in n by m has a subsequence say xn plus m has a subsequence xn plus m such that by using definition of Cauchy sequence we can easily construct this type of subsequence such that norm of xn plus m minus xn plus 1 plus m is less than 1 upon 2 raised to n. Okay, convince yourself that we can construct such a sequence by supplying the proof of this fact. Again, by using definition of infimum, which I stated, we can find a sequence yn such that yn belongs to xn plus m and it satisfies the property that yn norm of yn this holds for every n, yn minus yn plus 1 is also less than 1 by 2 raised to n. You note that we are using definition of infimum here. I have explained these things in detail in notes, you may refer to that. Yn belongs to xn plus m, yn plus 1 will belong to xn plus 1 m and it will satisfy this property. We can select such a vectors by using definition of infimum. This is infimum of what? Which set? Carefully try to understand this step. This is infimum of the set norm of xn minus xn plus 1 plus m, small m, where m belongs to m, and by using the second property in the definition of infimum, that for every epsilon greater than 0 there exists y belongs to s such that y is less than g plus epsilon. See, I am referring to the definition of infimum. So by using this property we can find such a vectors. Okay, I recall what we have done. We have taken a Cauchy sequence in n by m. Take a Cauchy sequence in n by m. By definition of Cauchy sequence, we can find a subsequence xn plus m of this Cauchy sequence in n by m such that this property is satisfied. By using definition of infimum of this is infimum of the set. I write it once again. This is infimum of the set norm of xn minus xn plus 1 plus m. I should write small m plus m, where m belongs to m. So by applying definition of infimum to this set, we can find a subsequence yn or a sequence yn such that yn belongs to xn plus m for every n and norm of yn minus yn plus 1 is less than 1 by 2 raised to n. For m less than n, consider norm of ym minus yn. I could write this as norm of, better let me continue in next line. This is equal to norm of ym minus ym plus 1 plus norm for the whole expression plus I'm adding and subtracting these vectors yn plus 1 and yn plus 2. Yn plus 1 minus norm of yn plus 2 and so on. So what will be the last pair in this sequence? It will be yn minus 1 plus I should say plus yn plus 1 minus yn. I hope it is correct. Yn plus 1 minus yn. Let me check it. Okay, I think it should be n minus 1. Okay, now use triangle inequality. By triangle inequality, this is less equal to norm of ym minus ym plus 1 plus norm of ym plus 1 minus ym plus 2, and last term will be plus norm of yn minus 1 yn. Then use this fact. So using this is strictly less than 1 upon 2 raised to m plus 2 raised to m plus 1 plus up to 1 upon, so yn minus yn plus 1, it is 2 raised to n. So I should write here 1 upon 2 raised to n minus 1. 2 raised to n minus 1. Okay. How many terms are there? This is a geometric progression with first term 1 upon 2 raised to m. Now how many terms are there? n minus 1 minus m plus 1. So there are n minus m terms. Number of terms equals to n minus 1 minus m plus 1. As we are taking difference, we have to add 1, so that equals to n minus m. So there are n minus m terms, and this is a geometric progression which begins with 1 by 2 raised to m. So by using the formula a 1 minus r raised to n upon 1 minus r, this equals to, first term is 1 upon 2 raised to m, 1 minus r, common ratio is 1 by 2, number of terms is n minus m, and 1 minus r, common ratio is 1 by 2. So this is equal to 1 upon 2 raised to m upon 1 upon 2 upon 1 upon 2, and let me keep the expression as it is, 1 minus 2 raised to n minus m. So this is equal to 1 upon 2 raised to m minus 1, 1 minus 2 raised to n minus m. This is going to be less than 1, so I can say that this whole expression is less than 1 upon 2 raised to m minus 1. Thus we proved that for m greater than m, for m less than n, or better let me say for n greater than m, we have the property that norm of phi minus phi n is less than 1 upon 2 raised to m minus 1. So it means that since this tends to 0 as m tends to infinity, we can say that this is a Cauchy sequence. So this fact implies that by n is equal, n runs from 1 to infinity. This sequence yn is a Cauchy sequence in n, is a Cauchy sequence in n. There is a slight correction in the statement of the theorem. I forget to write that n is complete norm-linear space. I just stated that n is norm-linear space, but you take into account that n should be complete norm-linear space. Then only n by m will be complete. This fact we need, you note that if n is norm-linear space, then n by m is norm-linear space. That is true. So if n is NLS, then n by m is NLS. But if you want to prove that n by m is complete norm-linear space, then n should be again complete norm-linear space. So please take into account this correction that n should be complete norm-linear space. So Yn is a Cauchy sequence in n which is complete norm-linear space. To be precise, I will say as n is complete metric space, as n is complete metric space, Yn is convergent in n. Yn is convergent in n. Then it is easy to observe that the sequence, it is a, remember that this is a subsequence of Cauchy sequence which we have taken in n by m. So it is easy to observe that the sequence xn plus m converges to y plus m if y is convergent. Can you justify this fact? Let me complete the proof with this justification. How can we justify that xn plus m converges to y plus m? So consider norm of xn plus m minus y plus m. Use the definition of difference of two cosets. First, this is equal to norm of xn minus y plus m. Use definition of norm. This is equal to infimum of norm of xn minus y plus m, where m belongs to m. As this is infimum, it will be less equal to every element of this set, and in particular I can take one element which is say yn. So this is less equal to yn minus y. I am replacing xn by yn. I can replace it by any element, any vector in n, and in particular I am taking m to be 0. So yn plus y 0, and this is less equal to norm of yn minus y. As yn converges to y, this tends to 0, hence this difference tends to 0 as n tends to infinity. Got the point? That this tends to 0, hence we conclude that this tends to 0 as n tends to infinity. So this proves that our claim that xn plus m converges to y plus m. Thus, what we proved, every Cauchy sequence, thus we proved that every Cauchy sequence in n by m, every Cauchy sequence in n by m has convergent subsequence, has a convergent subsequence. Hence, by definition of complete metric space, n by m is also, so n by m is complete metric space. This proves that n by m is complete metric space. If every Cauchy sequence has a convergent subsequence, then that Cauchy sequence will be convergent, and it is equivalent to say that every Cauchy sequence in n by m is convergent. So n by m is complete metric space. By sequential definition of complete metric space, we conclude this. Thank you.